18.7 Environmental Problems. List and discuss important environmental problems associated with groundwater. Like many of our other valuable natural resources, groundwater is being exploited at an increasing rate. In some areas, overuse threatens the groundwater supply. In other places, groundwater withdrawal has caused the ground and everything resting on it to sink. Still other localities are concerned with possible contamination of the groundwater supply. Mining groundwater. Many natural systems tend to establish a condition of equilibrium. The groundwater system is no exception. The water table's height reflects a balance between the rate of recharge and the rate of discharge and withdrawal. Any imbalance will either raise or lower the water table. Long-term imbalances can lead to a significant drop in the water table if there is either a decrease in recharge due to prolonged drought or an increase in groundwater discharge or withdrawal. See Geographics 17.1. Many believe that groundwater is an endlessly renewable resource because it is continually replenished by rainfall and melting snow. But in some regions, groundwater has been and continues to be treated as a non-renewable resource. Where this occurs, the water available to recharge the aquifer falls significantly short of the amount being withdrawn. The High Plains Aquifer provides one example, figure 17.26. Underlying about 111 million acres, 450,000 square kilometers, 174,000 square miles, in parts of 8 western states, it is one of the largest and most agriculturally significant aquifers in the United States. It accounts for about 30% of all groundwater withdrawn for irrigation in the country. Mean annual precipitation on the High Plains is modest, ranging from about 40 centimeters, 16 inches, in western portions to about 71 centimeters, 28 inches, in eastern parts. Evaporation rates, on the other hand, are high, ranging from about 150 centimeters, 60 inches, in the cooler northern parts of the region to 265 centimeters, 105 inches, in the warmer southern parts. Because evaporation rates are high relative to precipitation, there is little rainwater to recharge the aquifer. Thus, in some parts of the region where intense irrigation has been practiced for an extended period, groundwater depletion has been severe. Figure 17.26 bears this out. The U.S. Geological Survey estimates that since 1950, water storage in the High Plains Aquifer has declined about 267 million acre-feet, about 87 trillion gallons, with 60% of the total decline having occurred in Texas. Figure 17.26 High Plains Aquifer. The map shows changes in groundwater levels from pre-development, about 1950, to 2013. Extensive pumping for irrigation has led to water level declines in excess of 30 meters, 100 feet, in parts of 4 states. Water level rises have occurred where surface water is used for irrigation, such as along the Platte River in Nebraska. Based on U.S. Geological Survey. Subsidence. As you will see later in this chapter, surface subsidence can result from natural processes related to groundwater. However, the ground may also sink when water is pumped from wells faster than natural recharge processes can replace it. This effect is particularly pronounced in areas underlain by thick layers of unconsolidated sediments. As the water is withdrawn, the water pressure drops, and the weight of the overburden is transferred to the sediment. The greater pressure packs the sediment grains tightly together, and the ground subsides. Many areas illustrate land subsidence caused by excessive pumping of groundwater from relatively loose sediment. A classic U.S. example occurred in the San Joaquin Valley of California, where subsidence approached 9 meters, 30 feet, in some areas, figure 17.27. Many other cases of land subsidence due to groundwater pumping exist in the United States, including in portions of southern Arizona, figure 17.28, Las Vegas, Nevada, New Orleans and Baton Rouge, Louisiana, and the Houston, Galveston area of Texas. In the low-lying coastal area between Houston and Galveston, land subsidence ranges from 1.5 to 3 meters, 5 to 10 feet. The result is that an area of about 78 square kilometers, 30 square miles, is permanently flooded. Figure 17.27 That sinking feeling. The San Joaquin Valley, an important agricultural area, relies heavily on irrigation. Between 1925 and 1975, this part of the valley subsided almost 9 meters, 30 feet, because of the withdrawal of groundwater and the resulting compaction of sediments. Photo courtesy of U.S. Geological Survey. Figure 17.28 Land subsidence in south-central Arizona. In southern Arizona, heavy pumping has led to water table declines of up to 180 meters, 600 feet. This has triggered extensive and uneven permanent compaction of sediments and the formation of large fissures, cracks, in the ground around the margins of subsiding basins. Some rural roads have signs that warn of the potential hazard. Photo by Todd Shipman / Arizona Geological Survey. Outside the United States, one of the most spectacular examples of subsidence occurred in Mexico City, a portion of which is built on a former lake bed. In the first half of the 20th century, thousands of wells were sunk into the water-saturated sediments beneath the city. As water was withdrawn, portions of the city subsided by as much as 6 to 7 meters, 20 to 23 feet. In some places buildings have sunk to such a point that access to them from the street is located at what used to be the second floor level. Saltwater intrusion. In many coastal areas, the groundwater resource is being threatened by the encroachment of saltwater. To understand this problem, let us examine the relationship between fresh groundwater and salty groundwater. Figure 17.29 shows a cross-section that illustrates this relationship in a coastal area underlain by permeable homogeneous materials. Fresh water is less dense than salt water, so it floats on the salt water and forms a large lens-shaped body that may extend to considerable depths below sea level. In such a situation, if the water table is 1 meter, 3 feet, above sea level, the base of the freshwater body will extend to a depth of about 40 meters, 130 feet, below sea level. Stated another way, the depth of the freshwater below sea level is about 40 times greater than the elevation of the water table above sea level. Thus, when excessive pumping lowers the water table by a certain amount, the bottom of the freshwater zone will rise by 40 times that amount. Therefore, if groundwater withdrawal continues to exceed recharge, at some point, the elevation of the salt water will be sufficiently high that the salt water will be drawn into wells, thus contaminating the freshwater supply. This is called saltwater intrusion or saltwater contamination. Deep wells and wells near the shore are usually the first to be affected. Figure 17.29 Saltwater intrusion. Heavy pumping in coastal areas can cause encroachment of saltwater and threaten the supply of fresh groundwater. In urbanized coastal areas, the problems created by excessive pumping are compounded by a decrease in the rate of natural recharge. As more and more of the surface is covered by streets, parking lots, and buildings, surface runoff increases and infiltration into the soil is diminished. One way to correct the problem of saltwater intrusion of groundwater resources is to use a network of recharge wells. These wells allow wastewater to be pumped back into the groundwater system. A second method of correction is accomplished by building large recharge basins. These basins collect surface drainage and allow it to seep into the ground. On New York's Long Island, where the problem of saltwater intrusion was recognized more than 50 years ago, both of these methods have been employed with considerable success. Figure 17.30. Figure 17.30 Recharge basins. Much of Long Island, New York, is completely dependent on groundwater. To help maintain the water table and prevent saltwater intrusion, more than 2,000 recharge basins have been constructed. Recharge basins are used in many places, not just coastal areas. Photo by Alan Kressler. Contamination of freshwater aquifers by saltwater is primarily a problem in coastal areas, but it can also threaten non-coastal locations. Many ancient sedimentary rocks of marine origin were deposited when the ocean covered places that are now far inland. In some instances, significant amounts of seawater were trapped and still remain in the rock. These strata sometimes contain quantities of fresh water that people may pump. However, if fresh water is removed more rapidly than it is replenished, saline water may encroach and render the wells unusable. Such a situation threatened users of a deep, Cambrian age, sandstone aquifer in the Chicago area. To counteract this, water from Lake Michigan was allocated to the affected communities to offset the rate of withdrawal from the aquifer. Groundwater contamination. The pollution of groundwater is a serious matter, particularly in areas where aquifers provide a large part of the water supply. One common source of groundwater pollution is sewage. Its sources include an ever-increasing number of septic tanks, as well as inadequate or broken sewer systems and farm wastes. If sewage water that is contaminated with bacteria enters the groundwater system, it may become purified through natural processes. The harmful bacteria may be mechanically filtered by the sediment through which the water percolates, destroyed by chemical oxidation, and/or assimilated by other organisms. For purification to occur, however, the aquifer must be of the correct composition. For example, extremely permeable aquifers, such as highly fractured crystalline rock, coarse gravel, or cavernous limestone, have such large openings that contaminated groundwater may travel long distances without being filtered and cleansed. In this case, the water flows too rapidly and is not in contact with the surrounding material long enough for purification to occur. This is the problem at well 1 in Figure 17.31a. Figure 17.31 comparing two aquifers. In this example, the limestone aquifer allowed the contamination to reach a well, but the sandstone aquifer did not. On the other hand, when the aquifer is composed of sand or permeable sandstone, it can sometimes be purified after traveling only a few dozen meters through it. The openings between sand grains are large enough to permit